Good morning and welcome to this training session designed to help you prepare for the Microsoft AI Fundamentals Certification. My name is Dan and I'm a technology evangelist at Microsoft. Throughout today's session, I'm going to try and demystify the terms and demonstrate the skills that you'll need to sit the exam. This will include machine learning, artificial intelligence, and Azure Cognitive Services. Now, in the sake of transparency, I will be using the content and labs from Microsoft Learn. I'm simply condensing it down into a video to make it easier for you to consume. To that, the labs and demos presented are all available for you to try by following the URL on screen. This will help you gain a greater understanding of the subject matter and go on to master certification. Before we begin, let's take a moment to understand the skills measured on the exam. Now, the AI 900 certification is designed to test foundational knowledge of machine learning and artificial intelligence workloads and how to implement them on Microsoft Azure. The exam is intended for both technical and non-technical backgrounds, so don't expect to see any deep technical questions, but rather questions designed to test a general understanding of the subject matter. Topics will include machine learning and AI workloads, computer vision, natural language processing, and conversational AI. If you're following along, the good news is you won't need to install any special software. We can simply use the Azure portal and Visual Studio code spaces for our development environment. Setting this up is super easy. Simply head over to online.visualstudio.com and create a new code space by providing a name and the AI Fundamentals Git repository. Microsoft will then create the necessary services and configure the labs needed to complete the exercises in the course. With that, let's begin. So what is artificial intelligence? Well, simply put, it's the idea of software imitating human capability and understanding the world around it. Think about it. What makes you human? It's the ability to reason and make decisions from what we know. The ability to sense when things are wrong and then learn from past mistakes. It's the capacity to see the world around us, generating new data and communicating it dynamically through speech and text. This is what makes us human and what scientists and engineers have pursued for decades so that software can mimic these skills. Today, we are beginning to realize this dream, with many services reaching human parity in terms of capability and accuracy. Artificial intelligence has become embedded into our daily lives, amplifying human ingenuity and empowering us all to achieve more. At Microsoft, we have developed a series of utilities that can help you get started in building your own solutions. Solutions that, just like humans, can learn, interpret, understand, and engage. So let's look at some of the common AI workloads. We'll start with anomaly detection. Anomaly detection looks at historical data and then uses computational power to identify unusual changes. This could be fraudulent activity on your bank account or perhaps a problem with a Formula One engine as it races round track. What's more, these same processes could be used for prediction forecasting. Perhaps looking at historical data in patients to predict the risk of future issues or the preventative measures they could take to help avoid. This data could be from anywhere, even images. In fact, today, AI processes data from a variety of applications, from unlocking your smart device to detecting cancerous tumours in mammograms. And let's stick with our smart devices. By now, I'm sure that we're all communicating with them, setting alarms, reminders, and to-do lists via voice. It's technologies such as natural language processing that makes this possible, working alongside conversational AI to make the process fluid. At Microsoft, AI development is guided by a set of 6 principles. We believe that AI should be inclusive and treat all people fairly. To that, we need to ensure that the systems we build are subjected to rigorous testing so that they work as expected and respect the safety and the privacy of its end users. Furthermore, it needs to be understandable, ensuring that users are fully aware of its purpose and any limitations. following a suitable framework that ensures governance. In fact, Microsoft President Brad Smith said it best: "When your technology changes the world, you bear a responsibility to help address the world you've helped create." So let's now change focus and discuss machine learning. Machine learning is a technique in which you can use data to train a model that predicts unknown information. For example, suppose a bicycle rental company keeps records that include the weather conditions, temperature, and seasonal details for the days in which they've operated. They also record the number of bicycle rentals that they've had each day. The weather and seasonal characteristics for each day are called its features, and the thing that we want to train a model to predict, in this case the number of rentals, is called the label. Now, we often refer to the features as X and the label as Y. We can take this historic data and apply an algorithm to figure a function that fits the features to the label. In other words, the function calculates Y from X. The function we've calculated is the basis for your predictive model. So if you have the features for a new day but the label is unknown, you can use the model to predict the unknown label, which in this case is the expected numbers of bike rentals. This machine learning, where the label your model predicts as a numeric value, is called regression. Now let's look at another form of machine learning. This time, suppose a health clinic takes measurements from patients. This could include blood pressure, glucose level, weight, height, and so on. Additionally, each patient will be categorized as diabetic or not diabetic. The patient measurements are our features, and the classification of diabetic or not, that will be our label. We can fit the features and labels to a function that calculates the probability of a patient belonging to a particular class based on their features. In this case, the possible classes will be diabetic or not diabetic. When the features for the new patient are collected, the model we've trained can predict the probability that the patient is diabetic or not. Now, this machine learning, where the predicted label is a category or a class, is called classification. So far, we've seen examples of regression, where we use historic data to train a model to predict a numeric value, and classification, where the model predicts the class to which an item belongs. These are both examples of supervised machine learning, where we have historic data with known features and label values that we can fit to a function to train the model. Now, suppose you have data that consists of features like the measurements and petal counts of some flowers, but you have no known labels. You simply want to group your items together into clusters based on their similarity. In this case, the flower measurements are our X value and the Y value represents the clusters into which we want to group the flowers. We can use an algorithm to separate the data values into clusters based purely on the feature values, and the resulting model predicts which cluster each flower should be assigned to. Clustering models like this that are trained without a known label are examples of unsupervised machine learning. Regardless of the machine learning model we create, there is a typical process that we need to follow. Let's take a look. First, you need to get the data with which you're going to train the model. We call this ingestion. Then there's usually an iterative process in which you explore the data and prepare it for modeling. Data pre-processing includes steps such as feature selection, or in other words, identify the features that are likely to help predict the label and discard the others. Then, you might clean the data. For example, by finding errors and removing them, or immuting missing values with a suitable replacement. You might also engage in some feature engineering to derive new features from existing ones, and you should generally normalize your numeric features so that they're on the same scale. Then you can apply an algorithm to fit your prepared data and train a model and evaluate its performance. When you're happy with the model, you typically deploy it to a service. Then applications can connect to the service and use it to predict unknown labels from known feature values. So let's now see these machine learning models in practice. We'll start with regression. and in this demo we're going to explore how a car dealership might use the characteristics of a car to predict its likely selling price. If we think back to what we've just discussed, the characteristics of the car will be the features and the price will be the label. Let's jump in. So the first thing that we will need to do is create our Azure Machine Learning workspace. This includes a wide range of features to help data scientists prepare, train, and then publish predictive services. I'll create the service in a new resource group named AI Fundamentals, and then in the UK South region, I will go ahead and create a new enterprise workspace bearing the same name. I'm selecting the enterprise version so that I can make use of the designer interface. This is a solution that would allow me to work without needing to write any code. Once completed, I can begin building out my solution in the Machine Learning Studio. First, I'll need to provision my compute resource. Think of this as the development workstation that I can use to work with my data. I'll create a new compute instance named MLVM and then specify a standard DS2 virtual machine. Next, I'll create my compute cluster. These are the resources that will be used for the on-demand processing of my experiments. I'll name the cluster MLVM cluster and again select a standard DS2 virtual machine image, opting for 2 nodes. Finally, I will create my Inference cluster, an Azure Kubernetes service and deployment target for the predictive services used to train my models. I'll name the cluster Cub1 and place it in the UK West region, specifying a DS2 size in a 2-node dev test configuration. With our compute resources created, we can begin building our pipeline. This will begin with a data set from which we want to train our model. Now I'm going to be using a sample data set from the designer, which I will name Auto Price Training. I'll provide a short description and then assign my cluster as the default compute target. From here I will click on Data Sets and then under Samples select Automobile Price Data and drag it onto the canvas. If I right click, we can visualize our dataset output. Then if I select a column, in this instance price, you'll notice various statistics for the values. Let's look at another column, normalized losses. Now notice that as we review the column, we can see lots of missing data. This is going to limit its usefulness in predicting the price label, so we will want to exclude it from our model. To do so, we're going to add a data transformation, and I will achieve this by selecting the modules and the data transformation section. Once selected, I will drag the Select Columns in Dataset module to the canvas and place it just below our raw data before connecting the modules with a connector. Next, I will edit the column from the Settings pane and include all columns except Normalized Losses. From here, we will need to clean missing data, and I can do so by dragging the appropriate module into my canvas and connecting it to the Select Columns in Dataset module. I'll edit the columns and include the names bore, stroke and horsepower, then opt to remove the rows that do not have any data. Finally, I will need to normalize the data, and again we can do so by dragging the appropriate module into the canvas. From here I will connect to the Clean Missing Data module and set the transformation and rules for the column names that I wish to normalize. Now to apply the data transformation, we will need to run the pipeline as an experiment. This is achieved by selecting the Submit button and creating a new experiment, which I would call Auto Price Training. Now that we've prepared our data, we can begin our training pipeline. Now it's common practice to train with only a subset of the data. This is because we will need some later in which to test our train model. To begin, I will drag the module Split Data onto the canvas and connect it to our Normalized Data module. I will then specify the fraction of rows in our first output dataset and add the train model module onto the canvas. The model we are training is to predict a price value. To that, we will modify the setting to set the label column to price. This will be a numeric value, which is why we are using a regression algorithm. To achieve this, I will add the linear regression module to the canvas and connect it to the train model module. To test the model, we will score it. This will validate our data set. So let's go ahead and add the module to the canvas. From here we can train the model, and again I will do so by running the experiment on the existing one, auto price training. Once completed, we can visualize the results. And notice a new column named Scored Labels. This contains the predicted label values. To evaluate our regression model, we could simply compare the predicted labels to the actual labels in the validation dataset. But this is an imprecise process that doesn't provide a simple metric. Instead, we will add the module evaluate module onto our canvas and then run the pipeline. When completed, we can visualize the results. Let's take a moment to understand the metrics. Mean absolute error is the average difference between predicted values and true values. The lower the number, the better the prediction. Next, let's consider the root mean squared error. For this metric, the mean difference between the predicted and true values is squared, and then the square root is calculated. The result is a metric based on the same unit as the label. Relative squared error is a relative metric between 0 and 1 based on the square of the differences between the predicted and true values. The closer to 0, the better the performance. Relative absolute error is a relative metric between 0 and 1 based on the absolute differences between the predicted and true values. Again, the closer to 0, the better the model is performing. Finally, we have coefficient of determination, which is more commonly referred to as R squared. This summarizes how much of the variance between the predicted and true values is explained by the model. The closer to 1, the better the model is performing. Now let's look at how we can prepare our model to use new data. To achieve this, we need to create a second pipeline. This will perform the same data transformations for new data and then use the train model to predict label values based on its features. This will form the basis for a predictive service that we can publish for our applications to use. So let's go ahead and create a new pipeline named Predict Auto Price. Now we will need to make a few changes. Firstly, we will need to replace our training data set. This is because the pipeline assumes that the new data will match the schema of the original training set, including the price. This is obviously unintuitive in new car data for which the price prediction has not yet been made. We will replace the module with the enter data manually. I will also delete the evaluate model module and add execute Python script. Next, I will add some CSV data to include the features we're interested in. I will also remove any explicit uses of the price field from the select columns in dataset module. In the execute Python script module, I will edit the code so it will rename the scored labels to predicted price. Finally, I will submit the pipeline as a new experiment named Predict Auto Price, and once completed, visualize the results. Now notice that we now have predicted prices for 3 new cars. We are now ready to publish our pipeline so that our applications may use it. To do so, we're going to deploy to the Azure Kubernetes cluster that we created earlier, and we'll do this by clicking on the deploy button in the top right corner. Once deployed, we can go ahead and test our service. Now, we have a simple notebook running, and this will test the service, so all we need to do is collect the REST endpoint and the primary key from the Consume tab of our cluster and update our code. Then, when ran, we can see a predicted price has been returned. So let's look at building another supervised learning example, this time using the classification technique. Now remember, With this model, the algorithm is predicting what category or class an item belongs to. Let's go back to our diabetic example. As discussed, we said that a clinic might use the characteristics of a patient to predict their risk of diabetes. In this case, the characteristics of the patient are the features and the label is diabetic or non-diabetic. Let's jump in and take a look. Now, because we're running on top of our last demo, we already have the compute resources in place. To that, let's start by creating a new data set from a simple web URL. I'll opt to use the headers from the first file and then next through the wizard. When completed, I will create a new pipeline named Diabetes Training and select my compute cluster. Next, I will add my dataset to my canvas and visualize the dataset output. If I select the diabetic column, note that it contains two values, 0 and 1. These values represent the two possible classes for the label that your model will predict. A value of 0 meaning that the patient does not have diabetes, and a value of 1 meaning that the patient does. Next, we will begin adding our transformations. Let's start by normalizing our data by dragging the module into the canvas. I'll set the transformation to min-max and include all columns except the patient ID and diabetic label. From here, we will submit and run a new experiment named Diabetes Training. And once completed, we can visualize the transformation data set and note that the numeric columns that we selected previously have been normalized to a common scale. Next, we will add our training modules. Again, we don't want to use all of the data, so we will split it as we did before. We will add the train model module and then the two-class logistic regression module to our canvas. Finally, we will add the score model module to the canvas and connect appropriately. Now, we want to predict a diabetic value, so we will select the train model module and modify its settings so that we can set the label column to diabetic. From here, we will run the pipeline using an existing experiment and when finished, visualize the results. Now notice the two new columns, scored labels, which contains the predicted labels, and scored probabilities, which indicates the probability of a positive prediction. So let's now evaluate our model. Remember, the validation data we held back and then used to score the model includes the known values for the label. So to validate, we will compare the true values to the labels predicted. This will highlight just how well our model performs. Let's add the Evaluate Model module and submit the pipeline. When completed, we can visualize the confusion matrix. Now the confusion matrix for the model is a tabulation of the predicted and actual value counts for each possible class. In this instance, we see a 2x2 grid highlighting the predicted and actual value counts for classes 0 and 1. The top left box highlights the true positives and the bottom right the true negatives. This basically means where the predicted and actual values matched. The other cells show cases where the predicted and actual values differ, i.e. false positives and false negatives. We should also make note of the metrics to the left of the confusion matrix. These include the accuracy, which represents the proportion of the diabetes predictions the model got right, the precision or the fraction of cases classified as positive that are actually positive, and the F1 score, an overall metric that essentially combines precision and recall. Also notice that there's a threshold slider. And remember that what a classification model predicts is the probability for each possible class. In the case of this binary classification model, the predicted probability for a positive prediction is a value between 0 and 1. Now by default, a predicted probability for diabetes over 0.5 results in a class prediction of 1, where a prediction below this threshold means that there's a greater probability of the patient not having diabetes. So the predicted class would be 0. Now that we have a better understanding of the data, let's get our model ready for production. Like before, we need to create a second pipeline that performs data transformation for new data. We can then use the existing model to predict label values based on its features. I will name the new pipeline Predict Diabetes and modify my canvas. I'll remove the diabetes data set and evaluate model, and then add enter data manually and execute Python script modules in its place. I'll then update the data input and output section of the enter data manually module and add some script to the execute Python script module to rename the appropriate fields. With that done, I can run a new experiment named predict diabetes. Finally, we can publish our model for consumption, and I'll do that by pressing the deploy button top right. As before, I have a notepad in place, so I will grab the REST endpoint and the primary key of my Kubernetes endpoint and test my service. Notice that when ran, a predicted diabetes diagnosis is returned. So we've just seen two examples of supervised learning. In the first instance, we use regression to identify the predicted price for new cars, and then we use classification to group patients together based on their risk of developing diabetes. As mentioned before, these are just two of many methods that we can use to build successful machine learning models. In fact, if you have the time, why don't you explore this a little more? Head over to the URL on screen to build out a clustering model that will help you to identify penguins. Now remember, clustering is slightly different. This is unsupervised learning, and that means that you'll be building out your algorithms based purely on the characteristics or features of your dataset. But don't worry, the designer, workflow and training processes are very similar to what you've just seen, so I'm confident that you'll be just fine. If you're sticking with me, we're going to change focus and begin looking at some of the cognitive services offered by Azure. We'll begin with the computer vision service and then move into natural language processing and conversational AI. Let's begin. So as I mentioned before, computer vision is one of many pre-trained models that empower developers to create solutions that can see the world. Now obviously computers can't really see, at least not in the capacity that we can. But they are able to break down images and video into pixel values and then use numeric values or features to train machine learning models that can make predictions about the content. And if you think about it, we've just done that. We see firsthand what was involved with our car and patient demos. But by having these pre-trained off-the-shelf solutions, developers are now in a position to build AI applications both quickly and easily. To use computer vision, we have to create the necessary resources in Azure, and this could be one of two types. We can create a computer vision service, which is obviously focused on just one solution, or we can create a cognitive services solution, a more general resource that includes many other services. As a rule of thumb, if you plan to use multiple cognitive services and want to simplify administration and development, cognitive services is a great choice. Regardless of what one you choose, two pieces of information are critical. This is the endpoint and the authentication key. Let's now take a deeper look at the service. Computer vision can analyze, evaluate and generate human-readable phrases that can describe what was detected in an image. And depending on the content, this may be multiple results, but each will be listed with a confidence score that indicates how confident the algorithm is with the supplied description. These descriptions are based on thousands of recognizable objects and associated with the image as metadata. And if you think about it, this can be particularly useful if you want to index an image along with a set of key terms that might be used for a later search. Computer vision can also return bounding box coordinates, in addition to detecting brands, landmarks and celebrities. Again, this is determined by comparing the image against a database of popular brands, people and locations. If a known entity is detected, the service returns a response that contains the name, a confidence score and a bounding box for where in the image the detected entity was found. The computer vision service can also use optical character recognition capabilities, and this is used to detect printed and handwritten text. On top of this, the service can detect image types, color schemes, and moderate content for adult or violent and gory scenes. So let's jump into a demo and take a closer look. So the first thing that I will do is build my cognitive service resource. Again, this is a broad set of services that I can use for multiple solutions, so a great choice for our demos. I'll name the service MS AI Fundamentals and place it in the UK South region before completing the wizard. Once complete, I will grab the endpoint and authentication key and paste it into the code that's hosted inside my Codespace's environment. Now when I run the first exercise, you'll see an image is returned. And notice the description. Computer vision has predicted a woman standing in front of a store, and this is a confidence score of 91%. Remember, this is determined from the algorithm that's been trained from the thousands of images in its database. Let's try another. Again, we can see a description of a man and woman standing in front of a store, but this time you'll notice the confidence is a little lower, and this could be because the male image is slightly out of focus. Now let's grab a little bit more information from the service. If I try the first image again but request a little more detail, you can see that not only do we get a description, we also get key tags about what was detected alongside bounding boxes of where. So let's now use cognitive services to classify and categorize my images. Again, we built this model earlier using the machine learning designer, but we're going to opt to use the pre-built and more refined solution that's offered by Azure. Remember, this is supervised learning. We'll define a set of inputs or features, and from that we can calculate a probability score and predict a label. And if you think about it, this could be used in a variety of applications, from product identification to disaster investigation, or even helping medical professionals detect cancerous cells in patients. We perform image classification using the Custom Vision service. Again, this is much easier than when we wrote our own model and means that people with little or no machine learning expertise can create an effective solution. To train a classification model, we upload images to our training resource and then label them appropriately. Remember, we're going to need a bunch of images to train, and ideally those images will be from different angles. You'll also recall that the model training process is iterative. This means that some of the data is used and some will be held back to evaluate. This is indicated by the following evaluation metrics. Firstly, we have precision, or the percentage of predictions that were correct. For example, if the model predicted that 10 images are oranges, of which 8 were actually oranges, then the precision would be 0.8 or 80%. Recall is the percentage of predictions correctly identified, and average precision is an overall metric that takes into account both precision and recall. So let's jump back into another demo and take a look. We'll begin by signing into the Custom Vision service. From here, we'll create a new project named Grocery Checkout, select our previously created cognitive service, and then specify a food domain. Next, we can begin uploading our images and adding our tags. I'm going to add and tag apples, bananas and oranges, and then once done, I will train the model. Again, we will make note of the precision, recall and average precision before connecting to a URL to test our model. As you can see, the image has a label of apple and a probability of 99.9%. So now we've classified our images. Let's look at object detection. And you might be thinking, isn't that the same thing? Well, there are some subtle differences. Think of it this way. Image classification categorizes images based on the primary subject matter it contains. Object detection, on the other hand, goes further than this. It classifies individual objects within the image and then returns the coordinates by means of a bounding box. And this is useful when the image contains multiple objects such as the one shown on screen. Let's take a look and see how the training model works. I'll begin by creating a new project named Grocery Detection and ensuring that the type is set to Object Detection. Next, I'll add my images to the training model. Once uploaded, I can begin adding the tags to my images. Now notice how the system can identify the coordinates by presenting a bounding box around the object. Once I've tagged all of the images, I will train the model. From here I can begin testing, and as I add an image, notice the predictions returned. As you can see, the probability is high and the images are highlighted in red. but we're able to change the detection threshold if we need to. From here I can publish my model so that it can be consumed by my applications. So let's now think about face detection. Now this may not be the most flattering comment, but the face is simply an object, albeit a more complex one for the algorithm to distinguish. Now many algorithms will use your facial landmarks to train the model. This will include things like gender, age and emotional state. What's more, facial analysis can also be trained to identify a known individual, such as when you set up your smartphone to unlock it by simply looking. In fact, facial recognition is widely used today, from security to social media. Think about it. When you upload an image to Facebook, the service knows your friends and suggests the tags. This is all a byproduct of face detection and analysis. The face service on Azure currently supports the following functionality: detection, verification, similarities, and identification. It will also return a series of detected attributes such as glasses, age, emotion, and gender, in addition to higher level analytics such as image blur, exposure, and noise. Let's jump into a demo and configure the service. Again, our cognitive services have been set up so we can simply run the code. Now in our first example, we are simply asking the model to detect the faces in the image. And notice how it does this by using bounding boxes. However, we can ask for more detail, such as the unique ID that's generated with each detected face. What's more, we can ask the service to analyze the facial features and the expressions of the person in the image. Notice how this shopper is labeled as happy. But the algorithm can also do more. We can ask it to detect a face and then find similar faces in a database of images. Finally, we can ask the model to recognize faces. Again, this is similar to the examples I gave with unlocking your phone and posting images onto social media. To do this, we must simply register the name to the image, and then the model will compare the attributes and identify the individual on any future submissions. Now up until this point, we focused on images and the objects within. But I want to take a few minutes to discuss and demonstrate optical character recognition and machine reading comprehension. Now this is a combination of two services: computer vision, which reads the text, and natural language processing that makes sense of it. This is useful for applications such as note-taking, digitizing forms and scanning documents. It's also worth noting that the service provides two application programming interfaces: the OCR API, designed for quick extraction of small amounts of text, and the Read API for larger documents with visual noise. But we can also go one stage further with services such as the Form Recognizer. This uses OCR with predictive models to help automate the processing of data in a document. Now by default, the service uses unsupervised learning to understand the layout and relationships between fields and entries in your forms. When you submit, the algorithm clusters the forms by type, discovers what keys and tables are present, and associates the values from keys and entries to tables. Form Recognizer also includes pre-built models for unique form types, for instance business cards and receipts, as seen here. As you can see, the model extracts key information, including the time and date of sale, merchant information, alongside taxes, totals and more. Let's now change focus and explore natural language processing. Now NLP is at the core of many of the applications that we use today, from translation software to chatbots. NLP is helping us avoid spam, correct our grammar and monitor our social media. In a nutshell, the service combines the power of linguistics and computer science to create intelligent systems capable of understanding, analysing and extracting meaning from both text and speech. The first service we'll explore is text analytics, but we'll also cover speech synthesis, translation and language understanding. Now analysing text is a process that evaluates either a document or a phrase to gain insight. And humans do this easily. We can quickly understand the key phrases, tone and talking points, in addition to names and popular landmarks. Computers, however, have to be trained using an array of techniques. This includes things like statistical analysis, frequency analysis, in addition to stemming, encoding and vectorizing models. These techniques can be complex, but Azure offers pre-trained models that can determine the language of a document. It can also perform sentiment analysis, extract key phrases to determine talking points, and identify and categorize entities such as people, places, dates and times. This could be applied to detect sentiment of customers on social media, or help a document search application extract key information to summarize the content. Let's take a look. Now I have written the sentence, "Artificial intelligence is going to change the world. It's such an amazing time to be in computing, but we all have a responsibility to ensure that the systems we build are ethical and benefit all." As you can see, the language has been detected as English. Key phrases such as computing, amazing and AI have all been extracted, and the sentiment has been scored at 100% positivity. We can also see the named entities. These have all been identified as skills alongside a link that takes me to Wikipedia for further reading. But increasingly, we expect more from AI. And today we want computers, phones and smart devices to understand vocal commands. This kind of interaction requires two specific capabilities: speech recognition and speech synthesis. Speech recognition converts the spoken word into data that can be processed through pattern analysis. This is particularly useful for closed captioning, transcription and voice dictation. Think about your last Teams call, or how a PowerPoint presentation can now do real-time language transcribing. This is all down to speech recognition. Speech synthesis in many aspects reverses the process by converting text to speech. This is commonly used to respond to user input, provide interactive phone menus and broadcast announcements in public places. Let's take a look at the two services working together. Cortana. What time is it in New York?
It's 6:45 in New York.
Cortana. What's 384,000 times 12?
The answer is 1,008,300.
Cortana. Show me a map of Australia.
I found this for you.
Now there is no denying that technology has connected the world and somehow made it feel smaller. But as we build new relationships and collaborate with people from other cultures and geographic locations, the removal of language barriers has become a significant problem. Increasingly, automation is being used to address this issue. But to be successful, AI needs to not only understand the words, but also the context in which they're used. Again, Azure addresses this in one of two ways: through text translation or speech translation, or perhaps sometimes both. Let's take a look. Unfortunately, I don't speak any other language. Arguably, my English is terrible too. However, you can see that the service will transcribe my voice in real time. If I switch languages, you can see that the system will happily convert into any dialect I choose. Through the simple connectors, I can add the functionality to my applications with ease and provide this service to my customers and employees. So now that we've seen it working, let's build our own home automation application. Remember, to achieve this, we need to call on services that can understand vocal command. In Azure, this is called Language Understanding Intelligent Service, or LUIS for short. To work with LUIS, we need to take into account three core concepts: the utterance, entity, and intent. An utterance is an example of something someone may say. I would like to order a pepperoni pizza, for example. From that, we can determine the entity, a pepperoni pizza, and the intent, to order one. Let's jump into Azure and build our solution. We'll begin by creating a new language understanding cognitive service. I'll call mine AD Lewis and set my authoring, prediction, location and price points. Once created, I can sign into the portal and create a new app for conversation. I'll call mine Home Automation. With the app canvas created, I can add my entity. I'll add a new entity named Device and then list items for both fan and light. Next, I will create my intent. In this instance, switch on. I'll add two examples, firstly to turn on the fan and another to turn on the light. From here, I can then associate both with their corresponding entity. Once done, I need to repeat the process to switch the equipment off. Next, I will try a couple of test utterances. This will check both the intent and entities defined. When I'm happy with my service, I can publish to production. To do so, I will click on the Publish button in the top right hand corner and copy the application ID that is generated. This will be used to connect my app to the service alongside the Lewis endpoint and authentication key. From here, I can begin testing the app. And remember, I can use both text and voice, to which Lewis should be able to understand and respond.
Turn the light on.
Okay, so let's wrap up this session with one final example, Conversational AI. Now, have you ever tried to find some information from a website? To give you an example, I recently upgraded the speed of my broadband and I honestly spent more time trying to find the customer support number than I did switching service. And I'm not alone in this. Today, with company commerce largely online, the complexity and services offered mean that answers to specific questions are typically hard to find. Often these organisations find their support personnel being overloaded with requests, and this could come from phone calls, email, text messages, social media or indeed other channels. Increasingly though, they're turning to artificial intelligence solutions that make use of bots to provide a first line of automated support through the full range of channels. To implement this kind of solution, companies need two services, a knowledge base and a bot service. So let's jump into our final demo and build this out for a fictitious travel company. I'll begin by creating a new bot service named AI Fun Bot by setting the location and price point. From here I can select my Q&A service, my language and name my knowledge base. Now I'll be pulling down the Q&A pairs from the Microsoft Git repo by means of a URL. Finally, I will add the professional chit chat feature to my knowledge base and press create. Now as you can see, we have a number of question pairs, but I'm able to add my own to the solution via a quick edit as seen here. Next, I'll save, train and test my service by means of a simple web chat interface. Then when I'm happy, I can publish the solution. Do bear in mind that you'll need to provide a unique app service name, as this is a PaaS service and therefore dependent on DNS. I'll also disable application insights as it's not relevant for our demo. Now once published, I will again test in the portal. And as you can see, the service is working, so from here I can go into channels and then decide which services I wish to embed my bot into. Now we have covered a huge amount of technology and in a relatively short amount of time. Like I said at the beginning of the session, this has been designed to complement the materials on Microsoft Learn, and I encourage you all to visit the site, especially if you're pursuing the AI Fundamentals certification. It's my hope that you've enjoyed the session, and I invite you to head over to my website to see the other recordings I've done. With that, I wish you all the best of luck in your certification and look forward to seeing you again soon.